Alright, so this is a Penrose diagram. This is a white hole, and this is a black hole. This is a universe, and this is an antimatter universe. So you can think of a black hole as a point of convergence. That means no matter where you exist relative to this point, you're gonna converge to it. And you can think of a white hole as a point of divergence. So no matter where you exist relative to this point, you're going to diverge from it. These actually are very similar to the idea of a Mandelbrot set. So you have something like this in a Mandelbrot set. If you watch that video, the central point of this choroid has this property where some fraction allows you to develop a Fibonacci spiral that seems to have this property where the denominator of that fraction is always some step in between that follows a Fibonacci sequence. So it's like 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8. And so you get this with fractions, but you get an infinite amount of them within any space. You can get your own set of Fibonacci numbers. So the reason it's kind of like the black hole and the white hole, divergence and convergence, is because you can select within these spaces and they converge. This set of zeta squared plus c, which is an iterative function that just whatever you get out, you put back in, it converges to some number that is finite, and that allows you to define it in this complex plane. That means it converges kind of like a black hole. If you're out here and you're going to diverge to infinity, you're like a white hole. And so you can think of these as maps for how to embed black holes and white holes in projective space, although this is just one zeta function and there's many of them that should all exhibit similar properties. Okay. So I'm going to erase all that. That's important because when you look at these Penrose diagrams, you can think of this as infinite time in the future. So infinite time, and it's the future. And that's kind of like the infinite past. So time in the past. And this is space. Whatever you're inside of a triangle, you're in a constant speed of light. Speed of the light, or information in this diagram, has to travel at 45-degree angles. And so there is this idea that black holes emit Hawking radiation, and that just means that over time the space inside this black hole is going to converge to a point, so you can just imagine it collapsing in on itself. And it's evaporating away. And you can imagine this space as expanding. And so the trick is that normally you'd think these are the valid arrows. This is like light going backwards in time, or you could call it light, because if you saw one of my comments before, antiphotons are indistinguishable from light. And these are like going forward in time, and they're kind of like a new white hole in another universe. You have over here with the black hole in the universe and antimatter universe. So the reason this is important is because clearly this white hole can behave like a black hole if you just flip this diagram. And that flip is a Wick rotation. The problem is that's a Wick rotation in plane. There's actually 12 different kinds of Wick rotations that are associated to the kissing numbers. And that's something that kind of was intuitive to me, but I don't think, well, Penrose and Hawking had a system of imaginary time, but it's really 5-dimensional time. It's adding it's adding what's called the complex transform onto a set of equations in vector space, allowing you to get a degree of freedom for pictures, kind of like with the Mandelbrot system. If you saw that one video about that, you wouldn't be able to see that complexity if you didn't map it in complex space. But this is a little different because now let's think you're seeing the Penrose universes kind of from the side. You can imagine that these arrows which describe light can be going this way and this way, and you'd think, oh well, that's forward and backwards in time, that's all the possible ways that it could arrange itself. But it's actually, if this is an equilateral triangle you can think of, in a reference frame that allows you to do 45 degrees from each side, as well as outside of the plane. And so you can describe this as 12 symmetries. If you were to do 4 going down, 4 going up, 2 going forward, and 2 going backward, really it's like these are all going backward in time, these are all going forward in time, but in 3 dimensions you're doing a Wick rotation across this plane, say X plane, this plane, a Y plane, and the inside going into the board and out of the board, like if this was big, so it's closer, Z plane. And so if these are like ith Wick rotations, this is like first order Wick rotations, second order Wick rotations, third order Wick rotations. And so we know from the kissing number theorems that you have this, say this is a black hole. These are points of convergence, but these white holes are points of divergence. And so you get an equilibrium. In 3 dimensions you'd have 12 of these, and that equilibrium is described by these third order Wick rotations. And so a 4th order Wick rotation, I sub 4 you could call it, would describe 4-dimensional 24 kissing numbers, whatever. I'm not sure exactly how to map it because 4-dimensional space is strange, but you can actually imagine I sub n Wick rotations, which means you just keep doing more and more Wick rotations. And that's what allows you to have this strange idea of nested polytopes and Platonic and Archimedean solids that are embedded. So this all came from the idea of representing black holes and white holes as units of information. If you have a sphere and you want to put points on the sphere to represent these units of information, the best way to think about it is there's a lot of stuff going into this black hole, and along the surface there's this thing called the thermal field, which some physicists think to be a firewall, meaning there's information that can't really get past it. But it has an infinite amount of time to do that, so that's arbitrary. The real point is that even if you was no thermal field and you just shot one twister at the black hole, that would still take an infinite amount of time to reach the surface. So you can think of it as this idea of proper time, where this is the event horizon and these are twisters. There's this kind of musical idea of notes hitting each other, kind of like harmonies of, well, these are in different classes. They're moments in imaginary time. Because whatever this is in this like musical sheet, musical line in the musical sheets for whatever this harmony is, it represents some set of complex functions, zeta functions, on the surface of the black hole that you could just call them Mandelbrot sets just because that one's familiar. The point is, the information spirals in Fibonacci spirals, which when you see that one paper that I sent, is the most efficient way of distributing points across the sphere evenly. It just follows these Fibonacci spirals. And so it's the best way you can think of to encode these black holes and white holes on the surface of a black hole, for example. But what really happens when it hits it is you can think of this as a white hole. It's a point of divergence. You can think of these spots where it didn't hit as black holes. And so there's this evolving chaotic pattern on the surface describing these greater complex functions. The problem comes from the idea of, I call it entanglement reference frame, which is, let's actually go into the black hole. Say our information is encoded in some subregion of one of these Mandelbrots. Well, that region can be entangled to a different region, a different set. But these are limited in the middle by some inconsistent cohomology. Maybe they converge perfectly at sometimes, maybe there's a quantum superposition of where the points are that allows them to match very well. But there's still this cohomology, like the triangle. It doesn't exactly match when you look at all of it, but when you look locally, the pattern fits really well, like corners of that triangle. These three areas work really well, but when you look at all three together, they don't. So that actually comes from the problem of the hypersphere packing idea, the kissing number idea, and what's called nested polytopes. So the platonic solids, they're like the perfect equal-sided, equal-faced area 3D solids. So if you just draw like a hexagon, it's like the idea that you can have these structures that look in equal area, are able to draw it in 3D. Take this one off. Something like that. It's kind of hard to draw. But you have this sphere, and on the surface is where all this information is encoded. And this one might be entangled to this one might be entangled to this one. From the ER equals EPR interpretation, we know that means that something like a wormhole is being connected between them, and that gets connected in projective space. When you consider the complexity of the nearby regions, you get a lot of variation. When you get outside the complex region, it's completely unstable. And you're inside the complex region of the Mandelbrot set that's defined, it might be very stable. And so these divergent points are actually really important for creating the symmetries of the internal polytopes, these kind of shapes that match the middle. And so you might get these shapes embedded in shapes, embedded in shapes, embedded in shapes. And these are all going to draw a circle around each of these shapes, just like the first one. And those are like the sphere packing idea, the kissing number idea. And so you can think of if this system that's incredibly complex, once it's to a really small scale, appears just like a point making up Planck space. And you can describe these Penrose tilings as the surface of a black hole. Then you can kind of encode one of these Penrose tiles as just like a 1, and a 0, and this one is like a 0, 1, and a 1, 0, or some quantum state of the zeros and ones. Alternatively, in a Wick rotation, you can consider this one a 1, and this one a 0, and this one 1, 0, and this one a 0, 1. And in another Wick rotation, you can consider this one the 1, and this one the 0, and this one a 1, 0, and this one a 0, 1, and this one a 1, and this one a 0, this one a 0, 1, and a 1, 0. And so you can understand why there's 4 Wick rotations per plane. And a plane is really just one of these. So in the X plane there's 4, like I described here. In the Y plane, you get up, left, up, right towards you, and out, left, and out, right towards you, and also into the board, left and right to both directions. This state would describe all of the quantum bits required to measure a set of stable Planck spaces within a single imaginary instant. Now you take this over many of these tessellated Penrose diagrams, look something like this. And you imagine this kind of incredible music of twisters hitting this space, and the patterns that have to create for you to create symmetries between the states, because they'd have to represent in 2 dimensions, this hyperdimensional interpretation of ith Wick rotations in n planes or n dimensions. This is just an idea that I was using to explain why I called the left-sided universe the antimatter universe instead of parallel universe. Has to do with Dirac's equation. It's a little hard to explain. But here you have hyperchirality. So there's this idea that chirality is very simple. You have a system that goes like this, and you have a system that goes like this, and they're antichiral. But if you enable it to have a different state, Then it has anti-dual chiral properties. These are reflected by some mirror of symmetry. But when you give the chirality more dimensions, then the mirror has to have one more dimension as well. And so, in this case, you're thinking of these as three-dimensional spaces, and this is a two-dimensional mirror. And you're using the original interpretation of light cones, so like a Big Bang universe. There's this light cone signaling the transfer of information in our universe, and there's this anti-light cone describing antiphotons that went backwards in time from the point of the Big Bang. Really, we exist more like on a continuum where there's a symmetry. You can think of this as a light cone. Either way, it could be this way or this way, or this way or this way. So you can also be here. This one probably makes more sense because you're within the light cone, so you can see the symmetry better. That's the same thing. It's really just a wick rotation. See, this is actually describing a toroid. It's the inside of a toroid. It's like a toroid's like a donut. And so this is just like the inside of a toroid. This is like the black hole. So you can rotate this in the three planes that I was talking to you about, in and out. There's the y and x. And you get this kind of hypertoroid where it's in all possible angles. And then you get that complex structure of the E8 symmetry groups. And so, in that interpretation of these wormholes and the twist arrays creating white holes, enabling some distribution of pattern from that area, local area, that then is co-homologically consistent with some other area within that imaginary instant, means like the computational complexity is beyond anything you can really think of. The Huerta puzzle is an idea of least action. So if you know Feynman's integral path sum, there's the idea that the best way to describe the path of a particle is to use probability amplitudes. And you have to sum all the possible probability amplitudes of a particle within all of the possible wave functions that that particle could occupy. And when you average that out, you get the path of least action, or least resistance that the particle actually takes. So you need virtually infinite degrees of freedom to do that. And so there's a path of least action. Well, let me put this on y as max. Coming in and out of z. So there's a path of least action where in that imaginary instant there's a single state of all these Penrose diagrams along the surface. where you create a consistent system with, so let's say in some imaginary instant, you get 12 of these impacts of twistors, and they happen to be exactly on the points that you would allow for kissing numbers. On the spheres around it, you need 12 of them to have like an actual kissing number in 3 dimensions. I think it's 12. And so they all fell exactly in the perfect spot for that. There's these local kind of like Mandelbrot sets, and they have rules they have to follow based off the previous entanglement states of those spots on those Penrose tilings that got hit by the twister. So let's say this one was black, and that meant that these 3 were white, and this one was black, so those 3 were white, and this one was black, so those 3 were white, and then this one was black, so those 3 were white. And this one got hit by a white hole, so it had to turn white. Well, if this one's white, then these have to be black. If these are black, then this one has to be black, and this one has to be black, and this one has to be black. And so you flip the states of the system because of some consistency in the rules of the patterns in that imaginary instant that follow some projective space. Of course, these might be entangled to a different Penrose triangle in a different part of, say right here, of the sphere, and so it might require this state to match that one. And this one might be entangled to another one. And so this one might be entangled to this one over here. So because this one has to be dark in the center, that means this one has to be light in the center. So then that causes this picture to change. Because this one has to be light, so these go dark. And it just continues iterating based off whatever entanglement properties it had, which is called the entanglement reference frame. And it's kind of like saying, well, yeah, there's all these wick rotations, but I see this one as a black hole in my imaginary instant, basically. And so that's the Huerta puzzle. It's like this game, this puzzle, but in ith degrees of wick rotations, not just in this simple version of it. See if I'm assuming anything. Yeah, and so the idea you kind of had that was interesting is this idea of a sphere. So at first I also thought, well, there's probably higher points of density, of complexity here, pools of complexity, and less complexity here and more complexity here. Just because these are poles, it seems like that should be correct. But that's arbitrary. The poles could have been here, or they could have been here, if you just consider this a 3D sphere and this like the back of the sphere. Could have been any 2 points that are perfectly opposite by some line that crosses through that sphere and within the center of the sphere. Could rotate anyway. Would still be a viable set of poles. And so I called that hyperchirality. And it's actually required for you to progress through imaginary time to have hyperchirality. And so if every black hole has this property, and in projective space they are within these Planck spaces, because these triangles are Planck spaces on the surface of the black hole, then that means that this intuition's right about the increased density or complexity. But it doesn't mean when you average over imaginary time that the complexity is higher here than here. If you take those prime number distributions in those videos that I sent you guys, you'll see that primes, no matter what set you take them from, always occur in equal amounts, as long as you're looking through them within sets that contain them. Those spiral arms that I showed you guys in that one video kind of explains that. So these follow the rules of the projective space from each of these singularities on the surface. And you can think of the complexity as a measure of these primes. Really, primes are kind of symbolic of the minimum information you need to describe the evolution of states within that system, right? Because if you have these numbers, you can describe all possible operations of arithmetic. You don't need any more numbers to do that. And so that's the path of least action of this informatic state. It's following some kind of pattern like this. There's primes of states, Planckian states, this iterative system that allows you to maintain the greater cohomology of the system. And if you look at Susskind's ideas for complexity, which I kind of erased to get some space, complexity seems to rise, stabilize, and fall rapidly. Rise, stabilize, and fall rapidly. Like that. So it seems like when it gets hit by twisters, the Planck spaces quickly stabilize to this high point of complexity, where these are the least action states. It's figuring them out, and then it figured them out. Then it actually becomes very efficient and simple, and it forces it to have this quick increase. Again, I think of this as, this point is really important, because if a black hole does evaporate from Hawking radiation, and these do represent all the 45-degree angles that you can emit from a Penrose tile, and these do have these wick rotations in 9th dimension, but are easier to imagine for us in 3 dimensions, which then give us the 12 kissing numbers, kind of this image that I was talking about over here. Then you can imagine that there's some limit, according to the equations, where this black hole evaporates and it explodes, or just disappears. Clearly to me, that point is within a Planck space, like one of these Penrose tiles. And because of Penrose's CCC theory, the black hole actually becomes incredibly stable, because in this relative scale, this Planckian scale, it's the lowest temperature, lowest entropy object in that universe now. It's actually the boundary of that reality. So, therefore, it would have minimum complexity very quickly. And I think that's what's describing this fractal scale. It actually even describes the fractal scale as you zoom into one of these Mandelbrot sets from the surface. It's the complex projective space within that universe that we experience as universes being inside black holes, and as they shrink, they become these Planck spaces. And so there's still a few questions that need to be answered about. Let's say you have a universe and it has a bunch of black holes that just collapse into the Planck spaces, and they all have all this Hawking radiation being emitted in all these possible directions. These represent Wick rotation entanglements between the surface states of these black holes and other surface states that are internal projections to these black holes that are themselves whole universes that have this same pattern that's going on. And so, because in this interpretation, you can think of the photons and antiphotons as white holes or black holes depending on your entanglement reference frame. It's hard for me to think whether this universe really created these projective spaces inside these black holes to these other universes, or if these universes created this projective space, because causality doesn't work that simply. And that's because in imaginary time, when I was thinking of that idea of the twistors hitting the event horizon, this is an infinite amount of distance away, because space is infinitely curved here. So actually, this arrow takes the same amount of time from our reference frame as this one to hit this surface. So there's this kind of entangled state between this point and this point that evolves as more twistors come. That tell it the rules, these rules of iteration. Because it never actually hits, it just is entangled. And they kind of know which one's more entangled and which one's less entangled.